Hi everyone, my name is Madhulika. I am from Electronics and Communication Engineering. My roll number is 24951804448. Today my electrical circuits topic is ballistic saturation velocity modeling beyond Ohm's law. Ballistic saturation velocity modeling beyond Ohm's law. BSV, ballistic saturation velocity, refers to a phenomenon observed in the behavior of materials when subjected to high electrical currents, where the velocity of charge carriers reaches a maximum or saturation, beyond which further increases in voltage do not lead to a proportional increase in current. This is a crucial concept in the study of electrical conductivity, particularly in materials with high current densities. Traditional models of electrical conduction, such as Ohm's law, assume that the current through a material is directly proportional to the applied voltage with a constant resistance. However, at high currents or voltages, the assumptions of Ohm's law break down and more complex models are needed to describe the behavior of charge carriers. The concept of ballistic saturation velocity is one such model that helps explain this behavior in materials, particularly metals and semiconductors, where electron transport becomes dominated by ballistic motion. Introduction to ballistic saturation velocity. The ballistic saturation velocity (BSV) phenomenon arises in scenarios where the velocity of charge carriers, such as electrons or holes, increases linearly with applied electric fields up to a certain point, after which the velocity reaches a maximum. Beyond this saturation point, even if the voltage is increased further, the current does not increase significantly, as the charge carriers cannot accelerate any faster due to scattering events and intrinsic material limitations. In high current and high field regimes, the conventional Ohm's law V equals to IR, which assumes a linear relationship between current and voltage, no longer holds true. Instead, the behavior of charge carriers is influenced by ballistic motion, where electrons travel without scattering over relatively long distances before colliding with impurities of lattice vibrations. Limitations of Ohm's law at high currents. Ohm's law is widely used to model the electrical conductivity of materials under normal conditions where the material exhibits a linear response to an applied voltage. The law assumes that the current is directly proportional to the voltage and inversely proportional to the resistance. V equals to IR, where triple V is the voltage, III is current, and RRR is the resistance. However, at very high currents or voltages, the assumptions underlying Ohm's law begin to break down. Under these conditions, charge carriers such as electrons experience significant accelerations due to the applied electric field and their velocities approach on a saturation value. Understanding ballistic saturation velocity. The ballistic saturation velocity is the maximum velocity at which charge carriers can travel material under the influence of an electric field. This is determined by several factors including electron scattering. At high electric fields, electrons are subjected to collisions with impurities, phonons, lattice vibrations, and other electrons. As the field strength increases, the scattering events become more frequent, limiting the acceleration of electrons and preventing them from reaching velocities greater than the ballistic saturation velocity. Material properties. The materials properties such as the effective mass of the charge carriers, the density of states, the strength of electron found on interactions influence the ballistic saturation velocity. For example, in semiconductors, the electron saturation velocity is typically lower than in metals due to stronger scattering. Temperature. Temperature plays a significant role in ballistic saturation velocity. As the temperature increases, the lattice vibrations phenomena become more intense, leading to frequent collisions and a reduction in the average free path length of electrons. This can decrease the saturation velocity. Field strength. The strength of the applied electric field affects how quickly electrons are accelerated. At higher field strengths, the electron velocity increases until it reaches a point where scattering events dominate, causing the velocity to saturate. The saturation velocity can be described mathematically as V saturation equals to mu EV equals to mu EV saturation equals to mu E, where V saturation is the saturation velocity, mu is the mobility of the charge carriers, and triple E is the electric field. Ballistic conduction in semiconductors and metals. Ballistic conduction is especially significant in semiconductors and metals, where charge carriers experience various types of scattering events. In semiconductors, ballistic saturation velocity is crucial for understanding the performance of devices such as MOSFET, MOSFETs, metal oxide semiconductor field effect transistors, where high electric fields are applied to accelerate electrons through the material. As the voltage increases, the electrons reach their ballistic saturation velocity, limiting the current and affecting the device speed and efficiency. In metals, where charge carriers are typically free electrons, the saturation velocity is generally higher compared to semiconductors. However, even in metals, as the electric field becomes stronger, the electrons eventually reach a velocity where scattering dominates and the current no longer increases linearly with voltage. Applications of ballistic saturation velocity modeling. Understanding ballistic saturation velocity is crucial for several advanced technologies, including high-speed electronics devices like transistors, diodes, and other semiconductors-based components rely on the accurate modeling of charge carrier velocities to ensure their efficiency at high voltages and currents. Ballistic saturation velocity modeling helps optimize the performance of these devices by predicting their behavior under extreme conditions. 2. Power electronics. In power electronics, where high currents are common, understanding the limitations of charge carrier velocities is essential for designing devices that can handle high power without overheating or fading. Nanoscale devices. As electronic devices continue to shrink, size quantum effects, including ballistic conduction, becomes more pronounced. At the nanoscale, charge carriers can travel over long distances without scattering, and the modeling of saturation velocities becomes even more critical. Integrated circuits. Accurate modeling of ballistic behavior allows for the development of more efficient integrated circuits, ensuring that the performance of circuits does not degrade under high current conditions. Conclusion. Ballistic saturation velocity (BSV) modeling provides a more accurate description about charge carrier behaviors at high electric fields, going beyond the assumptions of Ohm's law. As current densities increase, materials reach a point where charge carriers cannot accelerate any further and the current becomes limited by the ballistic saturation velocity. Understanding and modeling these phenomena is critical for the design and optimization of high-speed electronic devices, power electronics, and monoscale technologies. The development of more sophisticated models, such as the Boltzmann transport equation, allows engineers to predict the performance of materials and devices in high-field regimes, enabling the continued advancement of modern electronics. Thank you.